Have you ever thought about the possibility of traveling from Russia to America by road? Well, it might become a reality soon. It's the kind of project that could redefine global connectivity. This massive project will stretch across the Bering Strait, linking two continents and opening up endless possibilities. But it's going to cost billions and face challenges like never before. So, why hasn't it happened yet? And what makes this such an insane and nearly impossible feat? Before we start, please make sure to support our channel by clicking the like button and following us so you won't miss any updates on the latest mega projects. The idea of linking Eurasia to America had been brewing inside the minds of engineers and visionaries alike for over a century. This concept came into being over 11,000 years ago, with ancient Beringia connecting the two continents. This natural connection disappeared as sea levels rose, but the dream of creating a man-made link remained. In 1892, American engineer Joseph Strauss proposed the first bridge across the Bering Strait, though the idea was quickly dismissed by the Russian Empire. A more serious attempt was made in 1904 when a group of American railroad tycoons proposed a tunnel, and Tsar Nicholas II gave initial approval. However, the project was shelved by 1907 due to political and logistical hurdles. In 2007, the project became active again as the Russian government initiated the TKM WorldLink project. The project proposed a huge railway and infrastructure network, which also included a 103-kilometer-long tunnel just beneath the Bering Strait. China took interest in the project and proposed a high-speed railway plan, connecting northeast China to America, spanning over 10,000 kilometers. Now, these massive projects also had some massive costs ranging from $65 to $105 billion. The time frame to complete these projects was estimated to be 10 to 15 years. With that aside, it's important to pinpoint the kind of technical and engineering challenges this project would face. The hypothetical bridge or tunnel would span around 83 kilometers across the Bering Strait, significantly longer than the Channel Tunnel, which connects the UK and France at just 31 miles. This extra length introduces substantial engineering challenges, particularly for maintenance and safety. While the Bering Strait is relatively shallow at an average of 50 meters deep, its seabed presents geological complications, including soft sediments and rock formations that make large-scale tunneling difficult. Unlike the more stable terrain under the Channel Tunnel, the Bering Strait poses shifting and unstable layers. Temperatures in the Arctic can reach 50 degrees, affecting both the durability of the materials used. This freezing temperature would make the steel brittle. As a result, extra precaution would be needed to ensure material longevity. Up to 6 feet thick, the ice in the Bering Strait poses a major threat to any structures built in the area. Ice flows exert immense pressure on bridge piers or tunnel entrances, which would need to be reinforced to prevent damage from constant movement and shifting. The brief Arctic summer only allows for about 5 months of workable conditions each year, from May to September, severely limiting progress and prolonging the construction schedule. In the harsh winter months, the area becomes almost inaccessible. The Bering Strait's located within the Pacific's Ring of Fire. Now, this area is known for its frequent earthquakes and volcanic activity. This increases the complexity of the project, as the tunnel or bridge must be designed to withstand significant tectonic shifts. Special engineering skills are needed to build structures that can move during volcanic activity and earthquakes. While the Channel Tunnel faced challenges with water pressure and geological instability, it was constructed in a relatively mild climate with predictable sea conditions. In contrast, the Bering Strait's cold, icy waters would require far more advanced technology to maintain stability during the tunneling process. The sediments in the strait are also more prone to shifting, further complicating the construction process. Specialized tunnel boring machines, TBMs, would need to be developed, capable of working in freezing, shifting seabed conditions. These TBMs would need to be adapted for both extreme cold and the movement of ice and sediment around the construction area, requiring significant innovation and technical prowess. The Bering Strait is one of the most isolated regions on Earth, with minimal existing infrastructure on both the Alaskan and Russian sides. To build a tunnel or bridge, engineers would first have to construct thousands of kilometers of new roads and railways just to bring supplies and equipment to the site. While the estimated initial cost of the tunnel is $12 billion, it can further push the total to over $100 billion in the process. This would include worker accommodations, machinery, transport networks, and shipping routes. All of these factors combine to make this one of the most expensive and technologically challenging infrastructure projects ever proposed. The vast distances, harsh environment, lack of existing infrastructure, and need for advanced materials and machinery create massive cost overruns. Moreover, with an estimated construction period of 10 to 115 years, the project would face constant delays due to weather conditions and potential seismic disruptions, further escalating the price tag. Securing the necessary financing and international backing for such a massive project also remains a significant hurdle. Investors may be wary of the project's viability and potential return on investment due to its complexity and the involved political dynamics. It's also important to discuss the building process of this tunnel in detail for a better understanding. Before construction begins, engineers would need to conduct detailed surveys using advanced sonar, seismic studies, and ice flow tracking to determine the safest route for the tunnel or bridge. These studies would help in mapping out geological hazards, such as shifting seabeds and earthquake-prone areas. Sonar systems would help understand underwater topography, while ice flow tracking systems would anticipate how ice formations might affect the project. Given the Arctic's fragile ecosystem, environmental impact assessments would be crucial. This would include studying how construction might affect marine life, ice flows, and local communities. These evaluations can take several years to complete and would need to secure international approval, adding to the timeline. This project would require collaboration between Russia, the US, and possibly China, due to its complexity and geopolitical implications. Negotiations could take years, as the project spans multiple jurisdictions and legal frameworks. Specialized TBMs would be used for this project. These machines, similar to those used in the construction of the Channel Tunnel, would need significant adaptations to handle the freezing temperatures, shifting seabed, and frozen ground, permafrost. Engineers would also need to build ventilation shafts on the Diomede Islands, located between Alaska and Russia, to provide safe air circulation during construction. Beyond transportation, the tunnel could also serve as a vital energy route. Engineers propose laying pipelines for gas and oil, as well as fiber optic cables and high-voltage power lines. In addition to the tunnel or bridge itself, construction teams would need to build significant above-ground infrastructure to support both the construction phase and future trade and travel. This includes highways, bridges, and possibly shipping ports on either side of the strait. While the initial costs of the proposed superhighway project are indeed significant, there are discussions regarding the long-term economic benefits, especially for freight transport. By facilitating trade between Asia and North America, this infrastructure could generate substantial economic gains, potentially offsetting the high upfront investment required. The idea is that a streamlined trade route would enhance efficiency, reduce shipping times, and lower costs for businesses involved in international trade. However, a comprehensive analysis is essential to evaluate whether these projected benefits would sufficiently justify the expenses incurred. Such analysis would consider not only direct financial returns, but also the broader economic impact on both regions involved. In conclusion, the ambitious plan to build a superhighway from Russia to America faces significant challenges across technical, financial, and geopolitical fronts. The extreme environmental conditions and high construction costs present major obstacles, positioning this project as one of the most daunting engineering feats of our time. However, the potential benefits, enhanced global cooperation and trade, are considerable. A successfully completed project could lead to new energy transmission avenues and stronger diplomatic ties among nations. So, will this colossal project become a reality? Or will it remain just a pipe dream? Only time will tell. Let us know what you think in the comments below. And don't forget to like, share, and subscribe to our channel.